Hello, everybody, and welcome to today's presentation, Consistency Without Clocks, Database Correctness at Scale, brought to you by FaunaDB. I would like to introduce you to our presenter, Chris Anderson. Chris is formerly a co-founder of Couchbase and architect of Couchbase Mobile. He holds a bachelor's degree in philosophy from Reed College and is an O'Reilly Technical Book author. He leads Fauna's developer community.
So thanks everybody for joining. I'll assume that you're interested in databases and even more so interested in how to achieve correctness at scale and what that looks like for Fauna and what that looks like in the larger ecosystem. So we'll be stepping through some of the actual transaction protocol that FaunaDB uses, as well as comparing it to some of the alternatives in a step-by-step, technical state machine kind of way. So that's one of my favorite things to show people is what the computer's actually doing, and this will be a chance to get in depth with that. So it's probably a good idea to go ahead and ask your questions when they come to mind, and don't worry about if I'm about to address it. It's always good for me to know what comes to mind when I'm talking about particular topics. So Fauna has been around for a few years, since 2012, and our mission is to build the database that that everybody wants here in 2018. And so rather than build something to scratch our own itch like a lot of the first generation of NoSQL databases, we've really asked ourselves, what do enterprises need? What do developers want? What's the feature set in an ideal database? And then set out to build that. So the hope is that for 80%, 90%, 100% of the projects that need an operational database, FaunaDB is the right choice. We are a relational NoSQL database, and by that I mean we combine the best of NoSQL with the best of relational. So NoSQL databases were created, in the last 10, maybe 15 years to get over some of the limitations of relational databases. If you've ever used a relational database at scale, you know that moving from one machine to replicas with failover to multiple machines in a cluster, each of those steps can introduce, not only operational complexity, but logical artifacts in the way that the guarantees that your database can give you. And what we wanted to do was build a database that didn't have those scalability thresholds where crossing them changed the way you interact with your data, but instead you get data integrity, ACID transactions, access control, all the things that you expect from a relational database, but all the way up the scale curve from just starting out for free to running, world scale. So you'll see how we do that at the storage layer in this presentation. And if you're interested in some of the other capabilities, like our temporality that enables audit logging, or our query language that enables complex precondition checks so you can run distributed ledger applications. All those features are covered on our website or in other webcasts. Today we'll be focusing on how the storage engine gets its job done. So first, I'll talk a little bit about consensus protocols, and I'll talk about the difference in how you can get consensus. There's two different approaches in the marketplace for scalable consensus protocols. So I'll talk about how FaunaDB does it, and then I'll talk about how Google Spanner and Google Spanner clones do it. Then we'll drill in on what Fauna does with our unified consensus and how the transactions themselves are deterministic. So what this means in practice is that we are deadlock free. And we'll talk all about that as we step through it. After that, I'll give a few examples of how customers are using Fauna in the real world, and then we'll have a conclusion and be ready to answer questions. So again, please go ahead and ask your questions as we're going so you don't forget them at the end. Professor Daniel Abadi did the foundational research that inspired FaunaDB, and he introduced a protocol called Calvin. So what you'll see today is closely based enough on the Calvin paper that you'll know Calvin after this. What FaunaDB does is inspired by Calvin. We have some additional optimizations and some implementation specific things that we do, but this Calvin protocol is essentially the mathematical alternative to what Spanner does, and we'll be talking all about both how it works and the consequences of it. So if you find this FaunaDB transaction protocol post on our blog, you can read a lot more about what Daniel Abadi has to say. We also have an on-demand webcast where he goes deep into Spanner versus Calvin, essentially this next section I'm about to talk about, but in great detail. So as we start to talk about consensus, let's talk about some of the guarantees that you would like to get from consensus. The simplest one to understand is linearizability. So what that means is that if you write to it a key, then any other reads that come along will see that write. And this, again, it applies to a single key and the operations on it. So this is usually what the C in the cap theorem is referring to, and it is the simple building block on top of which some of this other stuff can be built. So serializability is a little stronger of a guarantee in that it's dealing with transactions across multiple keys. And so if you have transactions that need to be isolated and check one key and update two keys, and you have those coming in from clients all over the world, serializability guarantees that the reads and writes associated with a given transaction are equivalent to some serial order of the transactions. It doesn't specify which. Strict serializability is one step up from that, and what it's saying is that if you write data to an item and then start another transaction in real world time, you should read the latest value and never have values rolling back in time. So strict serializability is sometimes called external consistency, and it's how your system can interface with other systems without giving data anomaly artifacts. Then the next thing, of course, is a consensus protocol. This is going to be a little bit different. It's an alternative to active passive or active active database replication, and we'll talk about that here. So before we get into these consensus protocols, it's worth noting that relational databases, and again, this is one of the problems that NoSQL set out to scale and that Fauna conquers, is with active passive replication, you've got changes coming in to one node and then being replicated to the secondary node. And if the primary node fails, then you can't go to the secondary node without losing some data guarantees, because you have no guarantee that the secondary has consumed all the changes that the primary node acknowledged to clients. So active passive replication can't give you correctness and availability. Now, active active replication seems like it should be the next step. The synchronous replication means that when you write to the primary, you don't get acknowledged until the secondary also commits. So it's a little bit, more sturdy in the sense that you're writing to two places, but it's a little bit more brittle in the sense that even if the secondary is unavailable, now the primary can't take writes. And so your availability is actually, twice as bad as it would be with a single node. So that whole quagmire is where most database replication lived until consensus protocols came onto the scene, in the recent past with things like Raft and Paxos, which we'll talk through in a little bit more detail coming up. But even within consensus protocols, and this is going to be the trade-off we'll focus on for this talk, there are unified consensus protocols like Calvin, and there are partitioned consensus protocols like Spanner. A unified consensus protocol has a single consensus log instance, one copy of the consensus protocol running per cluster. And it is a single logical transaction log that is appended to with batches. And there's no dependency to synchronize time among all the servers in the cluster. In partitioned consensus, you've got multiple consensus protocol instances, one running for each shard, or logically potentially for each key in the system. And the way to provide serializability is to look at the wall clock and wait until the uncertainty across the time of time across the cluster has resolved before you can commit anything. So this has some trade-offs, and more importantly, it has some hard and fast requirements if what you need is correctness. So the hard requirement is that you absolutely cannot have wall clock skew that goes beyond your pre-configured maximum error bound. So if the system has a VM clock drift or pause, or you smear your leap second wrong, or any stuff like that, you can end up with time discrepancy among your servers that is too great for the protocol to handle, and then you either have to shut down and become unavailable, assuming you can detect the problem, or you're going to accept writes without the serializability guarantees. And once you do that, all bets are off. You don't really have the guarantees that you were looking for in the first place. So in order for partitioned consensus to even work, you need to be able to put a strong bound on the wall clock error. So now we'll talk about what we do with our unified consensus, and it should be a little bit simpler how that differs from the partitioned consensus as we step through how it works. Again, if you're interested in looking at these diagrams on your own time, the FaunaDB transaction protocol blog that's linked here is a great place to get the details. And now is also a good time for our first poll question. So thanks, Billy, for putting the poll up. And I'll be curious to see what y'all have to say about this. Well, personally, I would be checking 3 of these boxes, but I won't tell you which.
I'll give a few more seconds for those last few responses. And here are the results.
All right. Well, that's interesting. It's fun to know that we're in an audience of folks who are using the Oracle DB2 MySQL stack. Also, it's not surprising to see Postgres, Mongo, and Cassandra showing up. I am a little surprised to see no one's using Spanner, but the price point isn't really set up for entry level, so maybe not that surprised. Well, let's get into how this storage system works. So I talked about the transaction log. Again, and the next slide goes into details, but what we have in Fauna is a single logical transaction log per database, and the segments that are appended to it are agreed upon in order by all the members of the cluster. Now, each of those segments, T0, T1, T2, T3, can contain multiple transactions, batches of transactions. So all the changes that came in a particular 10 millisecond window in our case. And one of the other key concepts that I haven't mentioned yet is multi-version concurrency control in the storage engine. For folks who haven't been database nerds for a long time like me, MVCC is a popular way to do database storage. What it means is that when you write new values, you're not erasing the old values or overwriting them. You're just writing something down next to them with a more recent timestamp. And this has a lot of benefits and opens up a lot of strategies for additional features of the database. So one of the obvious benefits is that if you have somebody who's doing a long-running read query that's associated with older versions of those records, it's running as an earlier snapshot, the writes don't have to wait for that read to finish before they can update the values. The writes can just go right ahead and write out new versions of these objects while the existing queries still query the old versions. So multi-version concurrency control means that readers don't have to wait for writers and writers don't have to wait for readers. But in the case of Fauna, it also allows us to offer snapshot queries as of old times. So you can grab a handle of the database and go look at, all the records as of T4 or T6 or T7. And that's a feature that we actively use in the transaction engine. So you'll see that coming up here. Now, how we do our unified consensus, we use a Raft-like protocol. And this webcast isn't meant to give you the details of it. If you follow those links below the figure, there are a ton of great online animations and ways to learn about how Raft works. The gist of it is that it is how these cluster members can all agree on the order of the transaction log without having to rely on wall clock time, and while being robust to partitions and other cloud outages and the kinds of stuff that you just have to be ready for in the cloud. So there's a few phases in Raft. It's important, I guess, to know that there's a leader election phase where an arbitrary node becomes the leader, and the leader sends out, all the writes go through the leader as well as heartbeats. And if the leader goes missing, then other peers start an election process so that they deterministically pick a new leader. And this also has the correctness guarantees that we need, because without a majority consensus, writes can't commit. So it works to provide a consistent transaction log with consensus ordering across all the cluster members. It's worth noting that this Raft system is designed for when you know who's in your cluster. So that makes sense when you have a single administrator, or other times when you can wrap your arms around the topology. It's not really designed for a peer-to-peer model where you have members coming to join the cluster and leaving the cluster, with an unknown amount. You need to know what you've got before you know whether or not you have a consensus quorum. So we talked about the transaction log and we talked about multi-version concurrency control, but just to get a little bit deeper into what's going on inside of FaunaDB, we also have within each replica site as many machines as you want. And so the data will be sharded, partitioned across those machines automatically for you in a way that avoids hotspots. And that scales out horizontally. So each cluster member, each replica site can have as many nodes as necessary to support the load. Additionally, because the only point of agreement is that transaction log, the replica sites could have different sizes. There's no constraint that the replica sites all have to have the same number of machines. You can see in the figure that multi-version concurrency control is included with the horizontally scalable storage. So if you look at node 2, widget ID is stored on node 2 with multiple versions of it in the figure. And then in node 1, it looks like widget ID 1 is stored, and it just happens to have a single version. So the actual storage is spread out evenly across the nodes in the cluster. in addition to having a scalable replica site, you can have multiple replicas. And this is the use case that FaunaDB replication really shines for on the wide area network, because it's got the minimum number of round trips. The latency that is imparted by the speed of light and the distance between your data centers is going to be at the theoretical minimum. So in our example here, which we'll stick with through the rest of this section of the talk, we have two replica sites. We have a San Francisco and a Washington, D.C. data center. It's okay to imagine maybe there's a European data center or an Asian data center that just aren't on screen. There's no constraints in the protocol about that. So we're looking at San Francisco and Washington, D.C. right now. And again, just to contrast to what goes on with Spanner, there's no atomic clocks in this situation. There's no waiting around for the clock to tick to resolve uncertainty windows. And even in the case of cloud outages or smearing your leap second wrong, kind of worst case scenarios, we offer the same strong guarantees that you need Google Spanner and atomic clocks and a team of dedicated site reliability engineers. But instead with FaunaDB, you can run it on commodity cloud hardware and get those same guarantees, which are much stronger than you would get from running partitioned consensus on commodity cloud hardware. Here is one slide to give you a summary of what this protocol looks like, and then we'll actually step through it. So the query comes in and it lands on an arbitrary node in the cluster. With FaunaDB, it doesn't matter which one, and we'll call that node the coordinator, which pre-processes the query and figures out what the write effects would be for that query. Then that whole kind of half done or basically pre-processed transaction is sent to the log and has a deterministic order in the log. Everything else falls out after that. Then what we'll do is rerun the transaction at the position in the log where it's going to be committed. If the underlying read effects have differed, then we know there's a conflict. Someone else has written a transaction that ran in the interim and usurped our position in the log. So the transaction that we're running as is aborted at the storage engine layer and can be retried at a higher layer. So this is deterministic and deadlock free because there is no coordination phase needed after appending to the log. Everything that comes out after you've appended to the log is completely deterministic and doesn't require any agreement among the cluster members. So let's walk through an example. We'll have this transaction, which is, there's two of them here. They're exactly the same. And what's going on is we have two customers that want to purchase the same item, and only one of them can win. And they're both submitting their purchase request to geographically dispersed replicas. So we'll have customer 2 try to buy widget 3 in San Francisco, and customer 6 will try to buy widget 3 in Washington, D.C. You can see that the transaction is exactly the same on both sides. Everything about it is the same except for the customer ID number. So let's see what happens when those transactions get submitted to the system. First of all, San Francisco will be the coordinator for customer 2's transaction, and Washington, D.C. will be the coordinator for customer 6's transaction. So the transactions come in, and the nodes do the reads locally at their local replica site to figure out which data is, the transaction is dependent on. So the reads are done and a buffer is created. The reads may need to be coordinated across, other shards in the replica site, and they're all read as of the current snapshot on that local replica site. So we get the latest version of customer ID 2 and the latest version of widget 3, and we write them into the buffer in San Francisco. And then in Washington, D.C., we get the latest version of customer 6 and everything else the same. So we have these two pre-flight transactions that are about to try to commit based on these reads. Before we even submit to the log, we can also calculate the write effects and buffer those into the transaction objects that's going to be sent in the log. So what we'll see is that both of these transactions result in widget ID's stock level dropping to 0. Now, one of them changes the store credit on customer 2. The other one changes the store credit on customer 6. They can't both be right, so let's see how the system decides which one gets to run. Well, here's the part where the raft magic happens. So San Francisco and Washington, D.C. both submit their transactions to the consensus protocol. And it's arbitrary what the ordering turns out to be, but it's going to be the same across every node in the cluster. So in our case, San Francisco came out ahead with T10, and Washington, D.C.'s got a transaction in the next batch, T11, but it could have been vice versa, in which case, we would still get our strict serializability, but we'd have a different winner. So let's step through then what happens after these transactions are committed to the log. The first thing that happens is the replicas validate the associated reads for a transaction. So in this case, the transaction that San Francisco submitted is validated by all the cluster sites, San Francisco, Washington, D.C., and any of the ones that we can imagine maybe off screen here. What happens is we have these reads that came in with that T10 transaction, and they were done at some time in the past because we didn't know we were going to be T10. T8 and T9 might not have even have happened yet when we did our reads. So we go, and now that we've been assigned to this point in the log, we have our original reads, and then since we know what our actual insertion point in the history is going to be, we do the reads again as of T10. And in the case where they match, then we're able to write everything out. So this is going to be the same, both in San Francisco and Washington, D.C. We'll pull up those same, the latest version of those same objects, and if they haven't changed, then our buffered writes can be written. So in this case, San Francisco and Washington, D.C. both see the transaction that San Francisco submitted as being valid, and the transaction can commit those buffered writes. Now we have in the multi-version concurrency control a new version of customer ID 2 and widget ID 3 with the timestamp T10 and the latest values. In this case, widget ID 3's stock level has been drawn down to 0. So that's what it looks like when a transaction commits successfully. But what about the other transaction that originated at the Washington, D.C. replica site? Well, the same thing applies. We're going to attempt to validate it, but in this case, it's stale. So every replica site will do the same thing deterministically. There's no coordination that needs to happen here. This just happens when the replicas apply the writes. So now that the Washington, D.C. transaction has been assigned a position in the log, T11 in this case, we'll go redo the reads as of T11 and pull in any values that may have changed in the interim. So we've got the original reads, and then we're redoing them. It looks like customer ID 6 still has the same timestamp and the same store credit, so that's good, but widget ID 3 has a new timestamp, and the stock level is 0. So these reads don't match. We're going to get the same thing happening at Washington, D.C., reading off of the scalable MVCC storage and see, oh, these don't match. And that means that we can't commit. Instead, the transaction's aborted. So the reads were different, and the transaction cannot be written out to storage from that T11 position in the log. So the error is propagated back up the stack, not all the way out to the user, but to the retry layer, which will then do everything we just stepped through again. It'll run new original reads, and in this case, the query will branch differently because there's 0 stock left of widget ID 3, and instead of trying to commit a purchase, it'll fail and say out of stock. So it gives the expected result by retrying at a higher layer. So again, it's important to note that this transaction abort did not require any coordination. The only coordination in the system is the ordering of transactions in this transaction log. Everything else falls out of it completely deterministically. Now, this is a simplification, what you're seeing here. We're pretending there's only one transaction in each of these log segments, but really there could be hundreds or thousands of them, however many came in the 10 millisecond window that corresponds to each log segment. And what that means is that as this is actually playing out in real life, you don't abort all of T11, you just abort one of the transactions inside of there. So the way to imagine the system under load is not whether T8 commits or aborts, but rather whether the transactions within that log segment commit or abort. So one of these segments might have 100% of transactions committing, another one might have 90% committing and 10% aborting. And if you had a high conflict workload, a worst case scenario, you'd still be committing to this transaction log with the same throughput as no conflicts, no aborts. If it was 100% aborts, you'd still be committing to the transaction log at the same speed. So there's no deadlocking. It's just a matter of if you have lots of concurrency, then some of these writes might show up and be no longer valid when they hit the storage layer. So it's just good to know about the underlying model. If the only kind of worst cases as far as impacting the throughput don't actually impact the the underlying machine logic of pushing the transaction log forward. So to recap how this impacts at scale, one of the most important things you get from unified consensus is no dependency on atomic clocks, and that's necessary to run in the cloud. If you try to run something like Spanner in the cloud without the invariants that are provided by Google's time infrastructure, then you don't get the guarantees that you might be looking for. So our deterministic transaction protocol not only gives you this operational simplicity of not needing to worry about how you smear your leap second, etc., it also gives you the correctness in the cloud, regardless of all those hiccups that we all have to deal with, like virtual machine pauses or other uncontrollable network latency anomalies, etc. So operational simplicity is on the one hand, and then on the other hand, what we get from the unified consensus model is this determinism, which we take advantage of in other ways in the system. So because we're writing out these append entries to the log, and they're basically immutable, we can do high performance snapshot reads. So reads that come in from a client that just want a consistent snapshot can get it right away without any coordination. They just grab a snapshot that is the latest one available on the replica, and they're able to do complex queries across that snapshot without any worldwide round trip times. By default, we do better than that. We offer read your own writes, and that's when you're connected to a particular replica site. So the replica sites will make sure that the clients always get a snapshot that they want, that makes sense for them based on the reads and writes they've done in the past. And it's also possible to ensure external consistency in a no matter what sense by using the database snapshot query feature to query the snapshot that hasn't happened yet. So you can do reads, from the current committed state if you need to, and that will give you external consistency and strict serializability. So the system gives the ACID guarantees, all the way, up and down there's no way to turn the consistency level down so low that you don't get ACID. And at the very high end, you get external consistency. No matter what, you get consistent snapshot reads. And by default, most clients get read your own writes, which is what most clients want most of the time. So we think this unified consensus protocol offers the kind of distributed consistency that developers and applications need from databases. And I think we might be right because people are using it for exactly that reason. So Nvidia is one of our earlier big customers. They've had 100% uptime since 2016, running really without a dedicated operational team. They've got an admin who works on other things as well. They're moving billions of operations a day, and they need to have ACID consistency because users don't want their identity to have the artifacts of eventual consistency. So user profile, password, that kind of stuff needs to be consistent. In terms of using the ledger and ACID capabilities to the fullest extent, it's great to see financial services firms like CapitalOne using us to essentially replace mainframe applications. So the data integrity and a lot of the features that I didn't go into much, play into this as well. But the data integrity that falls out of the deterministic transaction engine is what excited CapitalOne about FaunaDB, and they're seeing the kind of success that's causing them to expand their use of FaunaDB. Nextdoor is an interesting case because what they needed was flexible querying. They're mostly a Postgres application, but they do these push notifications that are a cross-cutting concern that need to be targeted to their users for all sorts of different reasons. And it wasn't playing well with the operational indexes on their Postgres. So they decided they needed to move it, offload that query to a more scalable system, and evaluated FaunaDB and decided it was a great fit for the particular queries they're looking at. It's kind of exactly what I would want to use the Fauna query language for, to fetch some records, do some logic on them, maybe follow some graph-like links to other records, query some indexes based on that, transform the results, and potentially save a summary, and do that all with ACID isolation. So because they can run those queries in FaunaDB with our quality of service scheduler, these complex queries don't interrupt each other and they don't put load onto their user-facing interactive systems. So to summarize, consensus protocols are the way forward. I talked about active-active and active-passive database replication and how they have fundamental flaws. So using a consensus protocol gets you over that and allows you to have availability, even in the face of cloud outages. But partitioned consensus, which is how Google Spanner achieves this, puts big requirements on your operational team to maintain an absolute bound on clock uncertainty. Because stepping outside of that bound, even for a moment, all bets are off on data integrity. Unified consensus protocols offer that same consistency, but they don't have the operational headache. And that's why we chose unified consensus for FaunaDB. So by putting unified consensus together with these deterministic transactions, the quality of service aware multi-tenant scheduler and multi-region replication, we have a database that is what the users like we just talked about are looking for. So if you're ready to move to the future and have a relational database that doesn't give you the scalability problems that you're familiar with from relational databases in the past, FaunaDB, I think, is not only the most correct option, but the most developer-friendly option. So go ahead and go on to fauna.com, sign up, send me an email when you play around with our example applications, and let me know how you feel about it. So here's a link to download the developer edition, which is just a jar file. We also have Docker wrappers, and we support Kubernetes and all that other good stuff. But it couldn't be simpler to deploy. And you can also get FaunaDB in the cloud with a free sign up and an ongoing free plan for your experiments. So thank you so much for listening, and I'm ready to take questions.
Awesome. Thank you so much for the presentation. We did have a few questions come in. Our first question is, do you support spatial data and spatial queries like PostGIS?
That's a great question. We don't have those GIS wrappers on top of our basic query engine yet. I've been doing databases for long enough to know how that layering works, and we have the the underlying stuff you would need, which is the ability to intersect an index on your x coordinates with an index on your y coordinates. So we can show you query patterns to offer bounding box style queries, and a lot of PostGIS is what's layered on top of that. So we're making strides in that direction, but we don't have those direct features yet.
Awesome. Our next question is, how can we try out FaunaDB? Is there a trial version that we can use?
So the jar that you can download from our website is the same bits that you go into production with as a licensed customer. And the license allows some evaluation and small deployment use. It should be enough for you to get started. And it's also worth noting that our cloud API is going to give you everything that you want as far as how your code would interact with the database. A lot of the stuff that would be, back-end administrator stuff in other databases is available in the developer API on FaunaDB. So FaunaDB Cloud is a great place to get started also.
Awesome. Our next question is, what kind of read and write latency can we expect when using FaunaDB?
In broad strokes, it's going to be similar for read latency to other scalable NoSQL databases like Cassandra, or we're essentially just dealing with the local cluster machine latencies there, and not wide area network. So reads are going to be as fast as comparable databases. Write throughput is going to be similar to comparable databases for the hardware that you deploy it on. And then where the real variable comes in is write latency. So write latency is going to be essentially determined by the speed of light between data centers. If your data centers are on other opposite coasts, then that'll add a few 40 milliseconds or so compared to if they're in the same data center or in different availability zones in the same region. So that gives you a tunable. If you need fast performance and can sacrifice regional redundancy, then you can run all your cluster members in the same region in different availability zones and get faster latency. If what you need is worldwide disaster recovery, then you can run your cluster replicas in different continents, and you'll have a little bit more write latency, but you'll get that additional redundancy.
Great. Our next question is, do you see any major differences between Fauna and Aurora?
Yes, that's an easy one for me. Aurora is going to look more like a drop-in replacement for a MySQL or something. It's also essentially scale up in that, as you're adding more, more throughput requirements, more performance requirements, your costs aren't going to increase linearly like they would with a cloud-based scaling solution. So the other big difference, is that FaunaDB runs wherever you want to run it. So you're not beholden to a single cloud vendor. FaunaDB Cloud runs, not just on AWS, but also on Google Cloud. So your data is replicated in both places, and you can have low latency access to it. So you could run ACID transactions in AWS that touch our AWS point of presence, and ACID transactions on the same data in GCP, and you'll get the consistency guarantees that I outlined.
Great. Our next question is, can you share some examples of other databases that use clocks for consistency?
Sure. I think that the other well-known clone of the spanner architecture is CockroachDB, and it suffers from a lot of the problems that I mentioned, especially because few of the CockroachDB deployments are going to have atomic clocks or be able to put hard bounds on their time uncertainty. So they can't offer the strict serializability or external consistency guarantees that Google Spanner, with its full operational support, or FaunaDB in any environment offers.
Awesome. Our next question is, you mentioned that consensus happens over a unified log. Can you please elaborate on this in terms of how this unified log is built and stored?
Sure. So in the database world, there's a concept of a write-ahead log. The idea is that once you commit to the write-ahead log, everything else that happens is there to support the read side of things. So you commit to the write-ahead log and the power goes out, or some other hardware failure happens, you're still good, because when you bring it back up for recovery, you'll be able to play that write-ahead log into the rest of the system and bring it up to date as of whatever was committed to the log. So that same architecture is what's going on with our transaction log. It's just that it's built using this consensus protocol, so it doesn't have to take an availability hit if one of the log member nodes dies. Instead, we elect the new leader and continue processing transactions. So if you want to look more at how that how that log is maintained, looking up Raft is a great way to do it. There's a ton of Raft visualizations. You can Google for the secret lives of data, and it'll give you a step through Raft simulator. If you've done that and you've still got questions about how the stuff is stored, then join us on our community Slack, and we'll be able to give you even more details.
Awesome. It looks like we have one more question. So audience, if you do have any more questions, please post those into the questions panel. The last question that we currently have is, which cloud platforms do you currently support?
Currently, we're deployed in AWS and GCP, but you don't have to be deployed in that cloud to connect with us. So writing code, for instance, Azure functions to talk to FaunaDB look just like Lambda functions, look just like if you had, some local code talking to FaunaDB. You just instantiate the client driver and write your queries. Of course, if you're running in the same cloud as us, then you don't have to pay the cloud provider, egress in the same way and all that important stuff. So there are some operational considerations, but from an application standpoint, you can connect to FaunaDB from anywhere.
Great. Well, that looks like all the questions we have. So Chris, would you like to add anything before I close things out?
This has been a great way to share the architecture with folks, and I hope you follow up. We have a ton of resources on our blog about, some of the prerequisites to what I talked about today, and then also more about what we do with the capabilities that I outlined.
Awesome. Well, I would like to thank you, Chris, for a great presentation today. I would also like to thank today's sponsor, FaunaDB, for providing the audience with a great webinar presentation. And lastly, thank you to everyone who attended today. We hope you learned something new that will help you in your developer career. Have a great day, and we will see you next time.